Hello friends, welcome to EC Academy.
In this lecture, let us understand transmission gate DC characteristics. Here, we are going to understand how the transmission gate works, focusing on their structure, operation, and the behavior of NMOS and PMOS transistors when they are used as pass transistors. First, let us understand the introduction to transmission gate. This figure shows the transistor connection for CMOS transmission gate. Here, this is PMOS and this is NMOS. These two are connected as shown in this figure with input V in and output is V0 and two control signals phi and phi bar. So a transmission gate is a complementary switch that combines both NMOS and PMOS transistors that are connected in parallel. This design improves the signal transmission. Each transistor has its own separate gate connection as shown in this figure, but they share common source and drain terminals. The control signal denoted as phi is applied to gate of NMOS and its complement phi bar is applied to gate of PMOS transistor. This complementary control signals ensures that one transistor is always on and other transistor is off. That will allow for effective switching. Now let us understand NMOS pass transistor characteristics. To understand the pass transistor characteristics, let us consider an NMOS transistor in transmission gate. The behavior of NMOS transistor can be analyzed based on the input logic V in when it is having the value VDD as well as 0. Now let us consider the first case where it is transmitting logic 1 when input is VDD. In this case, initially we'll assume the capacitor CL is discharged, which will be the initial condition, and V0 will be equal to 0. So this will be the initial condition. Now when input is equal to 1, which means Vin is equal to VDD and phi is equal to 1, the NMOS transistor will be on, and once NMOS transistor is on, there will be a path between input and output and it will start charging the capacitor CL. Here the current flows until the V0 approaches VDD minus VT. So here VT is the threshold voltage, and since V0 is limited to VDD minus VT, the transmission logic 1 degraded. This means the output voltage will not fully reach VDD across output V0. Hence it will lead to weak logic 1. Since VDD represents logic 1, but the output is limited to VDD minus VT. That's why at the output will not get complete VDD. That's why it will lead to weak logic 1. Now let us understand case 2 when the NMOS is transmitting logic 0. So this will happen when Vin is equal to 0. Now when Vin is equal to 0 and phi is equal to 1, NMOS will be on, and since input is equal to 0, there will be no current flowing between input and output. Hence the capacitor starts discharging. Since Vin is equal to 0, V0 will also be equal to 0. So we can say logic 0 is transmitted accurately in case 2. So in case 2, we will be having an accurate logic 0 without any degradation. Now let us understand PMOS pass transistor characteristics. Here the PMOS will behave as a complementary to NMOS, and the pass transistor characteristics of PMOS can be analyzed in two cases: when input is equal to VDD and when input is equal to 0. Let us consider the first case where the PMOS is transmitting logic 1 when input is equal to VDD. Now when VDD is equal to 1 and phi is equal to 1, at that case phi bar will be equal to 0, which is the control signal connected across PMOS, Hence, the PMOS will be on and it will start charging the capacitor CL. So here also the initial condition will be CL is discharged and output voltage will be equal to 0. Now, when the input voltage is equal to 1, since Q bar is equal to 0, PMOS is on. There will be a path between input voltage and output voltage. Hence, the capacitor starts charging. Here, the current flows between input and output until output voltage will be equal to VDD, which means the transmission of logic 1 is strong and it is accurate. So logic 1 is very strong and accurate since PMOS can fully pass VDD to the output because it is having negative threshold voltage which works in opposite direction that will allow complete high level. Hence, complete VDD is transmitted to the output voltage V0. Now let us consider the case 2 when PMOS is transmitting logic 0 when input is equal to 0. So when input is equal to 0, the control signal across PMOS will be equal to 0. At that case, the PMOS will be on. Hence, there will be no path between input and output. Current will not flow between input and output. Hence, the capacitor starts discharging. Here, the output voltage is limited to threshold voltage, which means the logic 0 that is transmitted to the output voltage will be degraded. Hence, summarizing the transmission gate, the NMOS is poor in transmission of logic 1, but it is good in transmitting logic 0, and PMOS is good in transmitting logic 1 and it is poor in transmission of logic 0. So individually these NMOS and PMOS are having the limitations. Hence, to overcome these limitations, we can combine these two transistors to form the transmission gate. Now let us understand the combined operation of NMOS and PMOS that will form the transmission gate. So as we discussed, to overcome the limitations of NMOS and PMOS, we can combine these two in parallel to form the transmission gate. So the transmission gate is a CMOS switch that will utilize both NMOS and PMOS complementary operations. So if we combine NMOS and PMOS, we will be having a complementary action which ensures both logic 0 and logic 1 are transmitted without any degradation. And we can have a good control, which means when phi is equal to 1, NMOS will be on and PMOS will be off. And when phi is equal to 0, NMOS is off and PMOS will be on. So when we apply phi is equal to 1, which will make phi bar is equal to 0. So this is the control signal across NMOS and this is the control signal across PMOS. Hence, both the transistor will be on. So combined operation of NMOS and PMOS is summarized in this table. So when phi is equal to 0 and phi bar is equal to 1, the NMOS will be off and PMOS will also be off. So for this condition, when input is 0, output will be high impedance, and when input is 1, output again will be high impedance. So to turn on the transmission gate, the condition is we need to apply Q is equal to 1. At that case, Q bar will be equal to 0. For this condition, both NMOS and PMOS will be on. So when input is equal to 0, then we will be having output is equal to 0, which is a strong output, and when input is equal to 1, the output will be strong logic 1 due to PMOS. Now let us understand the output characteristics of transmission gate. As you can observe, as input increases, the NMOS device resistance increases and the resistance of PMOS will decrease. Hence we can say the resistance of N device and the resistance of P device will influence the transmission. Hence, the transmission gate resistance is combination of both N device resistance and P device resistance that will ensure consistent voltage transfer across the transmission gate from 0 volt to VDD. This crossover point shows how a NMOS and PMOS will share the load, with NMOS dominating at lower voltage and PMOS is dominating at higher voltage. So the transmission gate design solves the individual weakness of NMOS and PMOS transistors by using them together. This ensures a robust transmission of both logic levels, making it fundamental building blocks in CMOS logic circuits that are used in VLSI design. This is about transmission gate DC characteristics. Hope you have understood the topic. Thank you.